Today's class, today's class is um applications of the double integrals. Okay. Well, sorry, on double integrals. I think we're going to need to focus on one type of problems. This is about the region. I have to drink some. Yeah, this is about how to find the center of a region, okay, in two-dimensional case. Okay. I look at this test. I notice that there's still some students do not prepare for the test yet. For example, the last problem, right? I did not ask you whether you have to use the polar coordinates to evaluate the double integral. But when you see a region which is like a portion of the circle, then the best way to do is to use the polar coordinates. So I want to talk about this problem first, okay, because we have enough time. Okay, so evaluate double integral, okay, and that would be, for example, y, okay, and the d is going to be the first quadrant of the circle, right? X is greater than 0, y is greater than 0. Okay, so okay, if you don't realize this, you can have to use a polar coordinates. You can try and set up an iterative integral. Okay, about iterative integral, I have to say that about 20% of students maybe still struggling with iterative integral. So if you are among them, please do more exercise or pay attention to what I'm talking about. Okay. So this is first of all, you have to draw let's set up an iterative integral first and try to evaluate. If you're not able to do that, then you change it. Okay. So this is a circle, right? Semicircle. That is a region. Okay. For the iterative integral, the integral for the integral outside integral, okay, and for the outside integral, and that will be always a number. It's not going to have variables. Okay, it's not going to have variables. So you must have like a 3, 4, those kind of things. It cannot be like one end is x, other end is going to be a variable. So this is very important. Okay. Well, okay. So how to do that? This is a 1. This is a 1. Okay. So if you want to use, let's set up 2 iterative integral. The first one, if you want to evaluate, it's with respect to x. Then you have to figure it out for what x, right? X is between 0 and 1, so from 0 to 1, okay? And that is x. And for each x between 0 and 1, then you look at the vertical line, okay? And you see what, how does the y change, okay? How does y change? And y is clearly between 0, and the top one depends on x. How does it depend on x? You can solve from this equation because this circle, the equation is x squared plus y squared equals 1. So you have to solve for y in terms of x. It's going to be square root of 1 minus x squared. So this should be 0. This is a 1 minus x. Okay. and in the y. Okay. Now you can evaluate this integral, in my opinion. Okay, but it's a little bit difficult. The reason is you have to use a substitution. Okay, you have to use a substitution. Then you can do. Okay, if you switch the order, if you want to switch the order, you cannot just switch this integral. Okay, without changing anything. Only for the intervals, you have to redo the problem again. Okay, and if you want to, that's the first one, that's the second one, right? And then you use you look at the switch into y should be outside. So y is a free right now from 0 to 1. Okay, but then x cannot be arbitrary, and you are going to use the horizontal lines, okay, to occupy all the whole region. So the points on the horizontal line, x will be changed. So for each y between 0 and 1, x is not arbitrary. Actually greater than equal 0, right? But there's upper bound for x. It's determined by that equation. You saw, the point on the circle is determined by x squared plus y squared equals 1. So you solve for x, you get square of 1 minus. Okay. So you will get 0. And here y, x squared plus y squared. Now this is difficult to evaluate. The reason is the reason is how to evaluate the integral of square root of x squared plus 1, right? Yeah. Okay. So I think the second integral, this is very difficult to evaluate. Okay. There's no standard formula. You can, if you look at the textbook, maybe there's a formula in the back side. The question, how do you evaluate the integral from a to b, like x squared plus c squared dx, right? That's my question. Okay. Okay, right? So you needed to face this problem. So it's not easy. Okay, but you can evaluate this type of integrals, right? By finding antiderivative substitution. Okay. Okay. It's still difficult, but it's easy to see how to do that, right? So this one you can, if you use x squared plus c squared, right? So then you have the upper bound, lower bound, right? So you can, it's a square of u, right? And then du equals 2x dx, so it'll be half of du. And what is the variable here? The variable here is going to be x is a, so a squared plus c squared, and a squared plus b squared plus c squared when x equals b. Then you find the antiderivative of this function. I think that this will be 2 over 3 u over 3 over 2. Okay, when you differentiate, okay, then that's 1/3, and then it's you plug them. Okay, minus a squared plus c squared 3 over 2. Okay, this is it's complicated, but you can evaluate. Okay, but if I use a first iterative integral, yes, I can do that. Finish that part. Then in the place of y, I get where's y? Y is down here. Okay, so you can finish this. Okay, it's a little bit complicated in substitution. Okay, and when y is 0, that's just x cube. Yeah, I don't want to do that. Okay, that's more complicated. Anyway, it can be done. So the best way to do is use polar coordinates. So this is a circle, right? Okay, it's in the x-axis, y-axis, and here you're going to use x equals r cosine theta, y equals r sine theta. Okay, clearly this is an arbitrary line, and here's a point x and y, right? Here's an angle. This is r. So clearly, r is between 0 and 1, theta is between 0 and pi over 2. So here's 1, here's r, here's theta. So you have a rectangle. That's your d bar. Okay. So the double integral over here is going to be go back to the double integral d bar, and right, and the y is going to be r sine theta, and here's a square root of x squared plus y squared is r squared, and then you have dr here and dA bar. Okay. So this double integral, and then it's easy to check. You can either, you have two iterative integral, either from r, right? It's dr, and then, and that is going to be r cubed sine theta d theta, or, and you can put a d theta outside, and this is the same function. Okay, doesn't matter which one you go first. You can solve the, you can evaluate the integral quickly. Okay, so let's see. Let's use this one on the left. Okay, and this integral of sine theta from 0 to pi over 2 is going to be 1. The reason is it's going to be negative cosine theta, right? Evaluate the two endpoints. So this is dr, so it's going to be integral of r cubed dr, and that's just 1/4 of r to the 4th power. Okay, so that's how do we do that? This is a problem on the test. Okay. Yeah, there are more students have troubles with the iterative integral. All right. So now we're going to talk about density and the center of mass. Okay. So if you have a given domain in the space, that's a D. Okay. And if you have the density function, okay, this is a defined on the domain. Okay. So the integral of the density function is going to be the total mass of this region. Okay, it's going to be the integral of, okay, right? If the density function is a constant, then this constant times the area. Okay, otherwise, yeah, it's given by this formula. Okay. Then we also want to find out. We also want to find out the center of mass. Okay, the center is not a geometric, geometric center. This could be somewhere because it depends how heavy of that, the region is different, right? So it's not homogeneous. Okay. So the center is coordinate x and y. That given by the integral of, this is the total mass, okay? And here is just the integral of x times the density function, okay? And similarly, you have this. So in order to find the center, you have to evaluate the three integrals. One is the integral of the density function. Okay, that gives you total mass. And then also the integral of the, you know, the function x times the density function and y times the density function. Okay. The reason this is, how do we find the 10? Okay. Well, this formula comes from the idea from the one-dimensional case. Suppose you have a coordinate line and you have put several points on this, right? Then the location here is the x1, and then you put, you know, it's a weight, it's the m1, x2, m2, x3, m3. So those are the weight of the point. Okay, then the total mass is going to be just sigma I from 1 to mi. Okay, but if you want to find the center of those points, what's the math, right? You needed to multiply by the coordinates, because the center may be here, x bar. Okay, so then the center x bar, and this is going to be m, right? So it's going to be m. Here's xi and mi. Okay. Yeah. So coming from this formula, and then use that when you can derive the above formulas. Okay. This is just one dimension. Okay. All right, so take a look. Let's take a look at the following problem. Okay. So the region is simple. It's just the square. X is greater than or equal to a and y is greater than or equal. Yeah, between 0 and a. Okay. And but this density function is going to be, yeah, the density function is going to be x. So this is a region. Okay, this is a region. Okay, this is a region. Okay, here's A, here's B. So yeah, if you look at this region, right? And I think this region getting heavier and heavier in that direction. Okay, because the density function increases. Okay, here's just like, you know, then and more, you know, much heavier. Okay. Yeah, we're gonna draw it. Okay, so this is a density function. So I guess the center will be not like the middle of. So before I solve the problem, I know the center must be on this line, the middle line. Okay, so what if it's the center of mass? Okay, will be x bar y bar. Before I do the computation by the symmetry, I can get some information here. Y bar must be half of b. I don't need a computation. Okay, I don't need to do any computation. But x bar should be greater than half of a. Okay. Why? Because the right hand side is much heavier. Right? Clear. So before you do the computation, you need to know something, right? So the total mass is going to be the double integral of d, right? And the density function x dn. All right, let's compute this first. I just said that find the center of mass is just, you know, 3 integrals. You have to be careful. Compute. Sometimes you can save your time, use a symmetry. Okay. All right, so this is a double integral. So this is a d and x dx. So I can use any of this, right? So I can put a dx outside, then this will be from 0 to, this is from 0 to a to dx, right? Okay. So first of all, x, well, it's constant with respect to y. Oops, where's my file? Okay, I hope it's back. All right. Yeah, let's all right, so it's back. All right, so this is the integral of x with respect to y. So it'll be x and y, evaluate b. So this is going to be b and x. And that is the entire derivative, half of. So the answer is a squared b. Okay. That is a total mass. Okay. Then you have to find out the x bar. X bar, you have to evaluate the integral. First, let's evaluate the integral with respect to x times the density function. Okay. So this integral will be d x times 0 dA. So this is actually it's x squared dA. Okay. So this time I'm going to put y outside, x inside. Okay. So the entire derivative of x squared is going to be 1/3 of x cubed. And I find out this just 1/3 of a cubed. Since this is a constant with respect to y variable, so I get this. Okay. And we also do the double integral of y with respect to, right? So this is going to be x times y dA. And you can use any of the variable first, right? Okay. So the entire derivative of the inside function xy squared, right? And then this becomes b squared here, dx. Then you again find the entire derivative of x. It would be this 4x squared b squared, right? And that is a 4 of a squared b squared. All right, so we're done. So the center x bar will be right on the formula first, right? Okay. So what do we got here? The new denominator is half of a squared b. Okay. The numerator is going to be 1/3 of a cubed b. You find out it's independent of b. Okay, and that'll be 2/3 of a. So it's greater than 1/2, right? So we predict 1/2 of a. Okay. Y bar, I should get half of b. So the numerator, yeah, this is a right to write down the formula. Okay, so this will be still half of a squared b. That's a quarter of a squared b. And after you simplify, is just equal to 1/2. Okay, independent of A and B. Okay. So that's how do we calculate the center of mass. Okay. Any questions? All right. Our next problem is from the book. Okay. These increased by the curves. Okay. And here's y equals 0, and y equals cosine x. And x is between -π/2 and +π/2. The density function is this time is going to be y. Okay. So we want to find out, we probably have to find out, the mass. Okay. Now we can also find out the center. Okay. Let's try. All right, so let's do this. Find the mass. Okay. So for step 1, you just draw the picture. Okay, what is the region? It'll be very important. Y equals 0 is the x-axis. Cosine x from -π/2 to +π/2 looks like that. It looks like parabola. Okay. So this is our region. This is our region. Okay. So write down the formula. This double integral of d rho dn. Okay. So for this integral, right? And it's a circle, right? Same, no, it's not a circle. So you cannot use the polar coordinates. Okay. So this is the integral, just the y, right? So how do you do that? I think you have to use a vertical line to cut through the region. Okay. So for each x between -π/2 and the +π/2, let's set up 2 integrals, okay? And then the y variable along this vertical line, the lower bound is 0. The upper bound is determined by the curve, which is cosine x. Okay, so this should be x, it should be outside from -π/2 to the +π/2. Then, right, this integral with respect to y. Okay, so this will be cosine x and dy. Okay. Okay, so and evaluate this integral. It's a 1/2 of y squared. We are okay, right? And that will be 1/2 of cosine squared x. Okay, how do you evaluate the cosine squared? You have to change it to there's a formula here, right? And cosine 2x equals 2 cosine square x minus 1. Okay, so you change it to that, and that is going to be, okay, that's going to be 2, that's 1b. That's another one. Cosine, oh my God. Have to be very careful about this. Okay. Okay, sorry. Yeah. So this is going to be integral from pi over 2 to pi over 2, and this is going to be 1/2 cosine 2x plus 1 and the dx. Right? Then you find the antiderivative of this function. So let's take 1/4 outside. The antiderivative of cosine 2x will be sine 2x divided by 2. And this just x. When you plug pi over 2 for x, you get pi in the 2 pi, right? So cosine pi is 0. So the first term is gone. The second term is pi over 2 minus negative pi over 2 is just pi. So it's pi over 4. That's it. Okay. Now, when you try to find the center, okay, this is y equals cosine x. For the center, right, you have to evaluate 2 integrals. One is this integral, is x, and y, right, dA, because the density function is y, okay? So this is the x bar. Y bar is going to be the double integral, and you have to put the y here, and then y times y. Okay. Now, I think clearly x bar must be 0 because the density function is like this. It's the density function is change horizontally, go up. No, change vertically, right? So the right hand side, left hand side, this region have the same density function. So the center must be on the y-axis, somewhere here. Okay. So this is the x bar, y bar. So x bar must be 0. So this must be 0. I don't even waste time to evaluate, but we can double check that. The y bar, I don't know whether it's in the middle of this. The top is 1. I'm not sure it's greater than 1/2 of, greater than half, 1/2 or less than 1/2, because yes, the density function is getting larger and larger, right? The value, but the horizontal line segment is getting short and short. So there's these 2 efforts cancel out, right? So I don't know. We can what you should do. Let's do the computation. Okay. So this double integral, it's y squared dA. We still do the same iterative integral, right? For each x, the y value is from 0 to cosine x, and here square dy. So now you get 1/3 of y cubed. Okay, you end up with the integral. Here's 1/3 negative pi over 2 positive pi over 2 cosine cube x. All right, do you still remember how to evaluate the cosine cube x? Actually, it's not that complicated. So let's find the antiderivative first. This is a standard trick. Okay. So the antiderivative will be you have to introduce a variable u equals sine x. So du is going to be cosine x dx. So this is going to be 1 minus u squared du. So it's u minus 1/3 u cubed. Okay. So this is the antiderivative. So you can say sine x minus 1/3 sine cube x plus c. So we use that. Then you find the value. Okay, d the double integral, right? Remember, this is going to be 1/3, and the cosine cube antiderivative is sine x minus 1/3 sine cube x, and evaluate at 2 endpoints. All right, so sine pi is 1. That's the first part, negative. Sine negative pi is -1, right? And minus 1/3 -1 cube. Okay, so actually this is going to be double the first term. First term is 2/3 doubled, right? 2/3 minus plus. So it's going to be 4 over 3 times 3 is 9. So 4 over 3 times. Okay, so y bar is going to be the double integral of this over the double integral of this, right? So it's 4 over 9 and divide by, what do we got here? Yeah, we got, I forgot. Yes. Oh, it's a, it is going to be pi. Yeah. Yeah, that's right. 1/4 of pi. Okay. So after we simplify, that is going to be 16 over 9 pi. Now, we have to check this number must be smaller than 1. Otherwise, it's going to be wrong. Okay, this is a smaller than 1. When you get the answer, okay, why is it smaller than 1? Just based on the picture, right? The center must be within the range, within the domain. So the highest point, the height is going to be 1. So it should be less than 1. Okay, and it is because this is about 16 over slightly larger than 27. So it's less than 1. Then we stop here. You don't need to waste time to get x bar. X bar is 0. Okay, x bar is 0. X bar is 0. Okay. Why x bar 0? By the symmetry. Okay. All right, so now we're going to take a look at the problem number 8. Has a domain D is bounded by y equals x plus 2 and y equals x squared. And the density function, I just choose a constant x times x squared. So the constant, well, yeah, you don't need to know the constant. Yeah, just let the x squared, okay? Okay, so step 1, you should find you have to draw the picture. Okay. Step 1, I have to draw the domain. So how do you draw the domain? As the parabola, it's easy to draw. Okay, then y equals x plus 2. Here's 2. So this line has a slope 1. So clearly there's 2 intersection points here. You have to find those 2 intersection points. right? So how do you find it? Well, just set they're equal because at the intersection point, they both have same y value. So x squared minus x minus 2 0. And you can quickly fact it. So you get x equals -1, y equals 2. When x equals 1, the y value is -1 plus 2 is 1. And this 2 plus 2 is going to be 4. Okay. So -1, 1, 2, and 4. Yeah, when x equals 2, y is 4. So you got those 2 points quickly. Why we needed that? Because we have to do the iterative integral. I needed to know the limits of the domain. Okay. All right, so you have to evaluate the 3 integrals. One is this, other one is this one, right? And this is going to be y rho dA. So let's do the first one. Okay. Then the first one, that is going to be x squared dA. Now, yeah, please write down 2 iterative integrals. No, only one, because otherwise it's more complicated. Why? You have to choose, you have to use a vertical line to evaluate the iterative integral. So it's easy, just take the difference of 2 functions, right? For each x, right? For each x between -1 and 2, the y variable of the y coordinate of the point on this vertical line, y is greater than the y value on the parabola, which is x squared, right? Less than equal to x plus 2. Okay, so that is so this gives you the lower bound x squared, upper bound x plus 2. Okay, right? Then the antiderivative of this is just x squared times just x squared times y, and then the difference of the 2 endpoints. Okay, so let's continue. That would be x plus 2 minus x squared dx. And then this is a polynomial, so everybody know how to evaluate. Right? How to evaluate. So you multiply this out. X cubed plus 2x minus, no, x squared minus 2 plus 2x minus x cubed. So the antiderivative is 1/3 x cubed plus x squared minus 1/4 x to the 4th power, and evaluate this. Right? I hope you can simplify it. Okay, so let's do it. Just be careful. Hold on, is there any mistakes? Let me check. Okay, I have a mistake here. So let me erase it. Yeah, this is when I multiply this out, because there's an x squared, not an x. Okay, so I needed to redo this part. I just realized. Okay, so x squared times x cubed plus 2x squared and x to the 4th power. Okay, then the antiderivative will be okay. Then evaluate the 2 endpoints. Okay. Okay, so how do we do that? Okay, let's 2 to the 4th power and the 2 cubed minus 1/5 and the 2 to the 5th. Okay, minus. We plug -1, so it's quarter, and here's 2/3. Minus becomes plus. So yeah. to do this, I think we have to be patient, right? Take the large common factor out, which is a 2 cube, okay? Take 2 cube out, you get 2 over 4 plus 3 over 2 minus 2 cubed. So actually the 4 over 5, okay? And I have to do, let me complete it, okay? Okay, so this is a good problem for the 5th grade student, right? Yeah, okay, so let's do the first 2, okay? I will get, let me see, I'm gonna work on the scratch bit, okay? I think that the first one is 8 times 11 over 30. Okay, the second one, what I'm gonna get, okay, I will get negative 13, so it becomes positive. Okay. Okay. So you get a common denominator, right? So 88 times 2 176, so it's 189. Not too bad, okay? So this, I hope my competition is correct, but this is a good exercise for students who claim it's graduate from elementary school, okay? Then should be able to finish this competition. Okay, within a minute. Okay, that's good exercise. Now, so we have we calculate the okay. It's not easy to compute. Then you have to compute each of them. I have to give up, right? So this is this is there are 3 different integrals here. We only did the first one. The difficult part is at the end. At the end you have to evaluate this. Okay, so if you want to do this, right? The only difference here is going to be the density function becomes, x cubed. Okay, so the integral is still the same integral. Let's set up the integral. X times rho will be x squared. No, x squared and square, so x cubed. Okay, x cubed. Yeah. So let's see. This still from x squared and x plus 2, right? And the function here is going to be x. Rho is x squared, so x cubed, and dy and dx. Okay, so the only difference here is x cubed, and this is x plus 2 minus x squared dx. And then you have to find out the entire derivative of this function to the 4th and 3x cubed minus x to the 5th dx. Okay, so the entire derivative is going to be x to the 5th plus 2 over 4 x to the 4th 1 over 6 to the 6th. Okay, evaluate the 2 endpoints. So this time I'm not going to finish the calculation. So I just put the number there. Okay, this is the first part. And the second part, that's be negative and the positive and the positive. Okay, so that is That is the numerator will be for the x bar. Okay. I hope the y variable will be a little bit easier. Let's try this first. Okay. So this will be the density function y times x squared, right? Okay, so it's from -1 to 2. Here still x squared and x plus 2, and y times x squared, and the dy and the dx. Okay, so the difference here is going to be, it's getting actually more complicated. The entire derivative of y is half of y. Okay, so it's half of y squared. Okay, as you can see that this is a half of x squared, and y squared is x plus 2 square minus 6. Okay. Okay, so this function will be different inside. If you expand it, you get x squared plus 4x plus 4 minus x to the 4th power. Okay, then you get polynomial. Okay. If you get polynomial, that's going to be 1/2 x to the 4th power 4x cubed 4x, and then you find the entire derivative. Okay. So this is a good place for people to use computers to do the computation, because we know how to do it. Just a little bit complicated, right? So it's not it does not get more information out of it. Okay, so that's so we just needed to enter the function in the computer, and then within a second you can get the answer right away. Okay, otherwise you have to manually do this computation, and finally you get the x bar and the y bar. Okay. Okay, so let me write down the last step. Okay, this is the entire derivative. Okay, it's going to be x to the 4th power, and here will be 2x squared 1/6 to the 6th. Okay, so I promise you to finish this. Okay, and here when you plug a -1, that's -1/5. That's a positive. Okay, so those are the very bad numbers. Okay, and then you write down the formula for the x bar and the y bar. Okay, and I think this is a really complicated problems. I only finished this in the math. Okay, and let's go back to this function. But when you get an answer, you have to look at where is possibly the center. I think the center possibly somewhere here. Okay, because you see, density function increase from left, it's 0 on the y-axis, but the left-hand side is smaller than the larger side, the right-hand side. So the center should be on the right side. So x should be greater than 0, x bar. Okay, this is an x bar, y bar. Okay, and so if we get a number, it's very strange number, and to see whether it's still, make sure this should be the center somewhere inside this region. Okay, if it's not, then there's computation mistakes. There is a computation mistake. Okay, so what I want to say that if I have to emphasize, this is you look at the symmetry of the region. Okay, if you look at symmetry of the region, don't use if it's already given a semicircle, then try to use the polar coordinates, because that will help you to solve the problem. Okay, so let me quickly mention the last problems. discussed the last problem. So the domain is going to be just the semicircle. Okay, and x y is greater than or equal to 0. Okay, so usually this is the type of problem we put on the test. Okay, I don't want you to do the very complicated computation. The density function is y. Okay, so find the center of map. Okay, this is kind of typical problems. But you look at the picture. Okay, this is a semicircle, right? And the density function increase like this. Okay, going in that direction, right? Increase. So this region, including the density, is a symmetric about the x-axis. Yeah, you write down the formula for the x bar, that's no problem. Okay, so this is going to be y, right? And y bar is here's y square dA. Okay, so clearly by you can say by symmetry, x bar should be 0. Okay, the center must be on the y-axis. So that saves you lots of time. All you have to do is just focus on those three integrals. And the y bar, I'm pretty sure, is between 0 and 1. Okay, right? Y bar must be between 0 and 1 because it should be within the center here, should be within the region. Right? Yeah, the center should be within region. So I needed to evaluate this y. Okay. Now this is a semicircle. Okay. If you use a usual iterative integral, that'll be from x's must be from -1 to +1 dx, and the y is going from 0, and the top with 1 square 1 minus square 1 minus x squared, and here's dy. Okay, not too bad. In this particular case, maybe you can even solve it, integral. The reason is you antiderivative the y squared, half of y squared, then you square of 1 minus x squared, and the radical is gone. So you will be half of y squared. Yeah, why is the top one square of x squared? Because for each x between -1 and +1, the y value is between 0 and 1, and the square of 1 minus x squared. Okay. All right, so this is the dx. And when you square the square of x, that's all you get. So that's easy to calculate. X minus 1/3 x cubed. Okay, it's evaluated to endpoints. All right, so what is that? This cannot be negative. Okay, be careful. Okay, it's going 1 minus 1/3. I think the other one is just double it, multiply by 2. Okay, can cancel it out. 2/3. 2/3. All right, good. So I needed to evaluate the other one is the integral of y squared. Now integral y squared, then be careful, right? And okay, if you still want to use this iterative integral, then you're going to have trouble. Why? Watch out. This is 1/3 of y cubed. You're not able to get rid of the radical. Okay, so when you plug square root of 1 minus x squared and the cube, and how do you evaluate this integral, right? So that's a problem. You still have to, yeah, there's a square root of that. So the question is how to evaluate this integral. There's no way you can do that. So, so the best way to do is use a polar coordinates, okay? The polar coordinate for the epicenter x equals r cosine theta, y equals r sine theta. Okay. Using that, then you will see that I is between 0 and 1, theta should be between 0 and pi. Okay. So our integral here is going to be something like that. Okay, it's a rectangle. Okay, here's the 1, here's theta pi. Okay. So this domain is sent to D by that transformation. Okay, so the integral, this double integral on this side is going to be the double integral on this side, which is y equals r sine theta square, and what is else? No, then that's the dA bar. Okay. Yes, you can get the iterative integral, and you can do theta from polar outside and r inside. That's fine. R cubed sine square theta dr and d theta. Okay. So the entire derivative r cubed is going to be a quarter of r to the fourth power. Okay, so you can evaluate, right? And finally, you get a quarter of sine square theta d theta. Now this one you have to still use the double integral formula. The double integral formula. The formula we have is cosine 2 theta equals 1 minus 2 sine square theta. So you solve for sine square theta, you will get 1/2 1 minus cosine 2 theta. I think a cosine 2 theta integral is going to be 0. Okay, I don't need to waste the time here. So that will be theta between 0 and pi, which is going to be pi over 8. Okay, I got those two numbers. So now, what is y bar? Y bar is the integral of this, right? And what do we got for the other one, the denominator? We got, right, 2 over 3. 2 over 3. So we have to simplify. 2 over 3 will be 3 pi over 16. I want to make sure this is smaller than 1. Okay, otherwise something's wrong. Okay, the reason is this is a circle, right? The center must be somewhere here. Okay, center must be somewhere here. And this is a 1, this is a 1, this is negative 1, right? Okay. And it's indeed smaller than 1 because pi is 3.14. 14 times 3, 3.14. It's less than 10 anyway. So it's less than 10. And the 10 over 16 is less than 1. So that should be correct. Yeah. Okay. So it's nothing new here, just the definition of the center. We're not going to talk about other topics in this section. Okay, the moment of the inverted of probability, for example, involve the integrals, expected values, all this kind of thing. So we just focus on the center here. Okay, it's more geometrical and more mathematical. Yeah. Okay, and so the homework assignments also only involve this. Okay,